Okay, so today we're going to continue to talk about linear and angular kinematics. Okay, so let's go ahead and think about what symbols. Okay, so we're thinking about what symbols we have for linear and angular position, velocity, and acceleration. Okay, so let's do linear first. So for linear, and again, I encourage you to fill this out yourself and then check back in on the video. So linear position will oftentimes use x, and oftentimes we'll measure that in meters. Linear velocity, we'll call that v most of the time and measure that in meters per second. Linear acceleration, we'll do a oftentimes, and meters per second squared we'll oftentimes use for that. Again, you can use other units like feet per like hour, whatever it is. That's typically what we'll use in physics classes. Okay, so now let's go ahead and go to angular. So for angular position, we just talked about, again, that was going to be theta, and that is what we'll oftentimes measure in radians, or it could be degrees, or rotations, or revolutions. Any of those things would be totally okay. Okay, angular velocity, that is omega. And again, that's lowercase omega. And that is oftentimes we'll measure in, like, that's a speed. So some angular distance per some angular time. So I'll oftentimes do radians per second. Sometimes you might do RPMs, which that is revolutions per minute. Again, you could write it as that, revolutions per minute. It could be degrees per hour, whatever you want, etc. And then the last one is going to be alpha, which is our angular acceleration. And again, we'll oftentimes use radians per second, or per second squared. It could be revolutions per minute squared, etc. And again, we will oftentimes with angular things just put it in radians per second squared. Sorry, radians and seconds for our units of position and time, just because that's pretty typical. Cool. So let's go ahead and chat about our constant acceleration equations. So what I want you to do is, from memory, it's good practice, write down those three linear constant acceleration equations. So go ahead and write those on down. Okay, so after you've done that, I'll write them down. So we have Vf equals Vi plus A delta T. We have Vf squared equals Vi squared plus 2A delta X. And our last one, delta X equals Vi times delta T plus 1/2 A times delta T squared. Perfect. And now, I bet you know what's going to come next. Guess what we're going to have? We're going to have good old angular constant acceleration equations. Gosh, that is fun. So angular constant acceleration equations. Cool. So go ahead, take a guess what those equations are, and then you can check back in on the video. Cool. So I bet you had a lot of great guesses. Let's think about it. So instead of Vf, now we're dealing with, so we're basically replacing V with omega. So this is going to be omega F equals Vi, we're going to replace with omega I, plus A is going to be alpha. So alpha times change in time. Cool. Instead of Vf squared, we'll do omega F squared. Vi squared will be omega I squared plus 2A is going to be alpha. X is, so X is replaced with theta. And so then we have change in theta. Cool. And let's see, delta X, instead of X, we got theta. So delta theta. V is omega, so omega I, time is just always time, plus 1/2 A is now alpha. And I kind of like, A and alpha look similar to me. Like alpha looks kind of like an A, which I find helpful. And T is just T. Cool. And these are our angular constant acceleration equations. Oftentimes, we will use the units for all these equations as radians per second or radians per second squared. But as long as you're consistent with your units as you plug in, you'll be good. Cool. Let's go ahead and solve one or two problems together, and then you'll be out of this video. Okay? So let's go this problem. Again, I encourage you, read the problem yourself, try it yourself, and then check back in on the video. But just as a hint, we are going to, first thing we do when we solve constant acceleration equations is rewrite down our list of givens, whatever we know we're dealing with these, and then you can go ahead and take a guess what your givens are. Cool. So I'm going to go ahead and do it after you've taken a guess yourself. Okay, so a Powers plant turbine accelerates from rest at 0.5 radians per second. Okay, from rest, so I know initial velocity is radians per second. It accelerates at 0.5 radians per second squared. Okay, that is going to be units of acceleration. So, and that's the rate of acceleration. Put that in. How long does it take it to reach its 3,600 RPM operating speed? Again, RPM stands for revs per minute. That is a velocity. That's its final velocity that it's reaching. So that is going to be what? Revs per minute. Cool. And we want to find what? Change in time. Cool. Let's do it. Okay, so check your units before you get started. So we have radians per second squared in 2 of the units. So let's convert the revs per minute to radians per second to match. You go ahead and try it yourself and then check back in on the video. Okay, now let me try it. So revolutions, let's see. 1 revolution is going to be, how many radians? 2 pi radians. Okay, revolutions cancel. Now let's do minutes to seconds. 1 minute is going to be 60 seconds. Minutes and minutes cancel, and then we're going to go ahead and be cool. And I got 376.99 radians per second. Okay, so now let's pick our equation. So we have omega I, omega f, alpha, and t. I just go through from the top to the bottom. So the first one, oh my goodness, that was silly. Okay, we're back. Cool. Omega f, I know that. Omega I know that. Alpha, I know that. Delta t, I don't know. Perfect. There's only one unknown. Let's use that equation. So I always write down the equation above. The AP exam and oftentimes tests, they will give you credit for writing down the correct equation. And then we can see like the beautiful story and help find any silly mistakes too, if we know what equation you're using. So let's put down our givens. So we have 376.99. Omega I is 0. Alpha is 0.5. We want to solve for delta t. Cool. And I get delta t. And again, I get 753.98 seconds. Cool. I'll do one more problem just for fun, and then you'll be out of it. So let's go ahead and look at this problem. So we have a merry-go-round starts from rest. Oh, wow. So many things are starting from rest. Okay. Omega I, 0 radians per second, and accelerates with an angular acceleration of what? 0.1 radians per second squared. Okay, for 14 seconds. Seconds, that's the time. How many revolutions does it make during this time? So revolutions is how much it's rotating, which is a change in position. So that is going to be r theta. Cool. Let's pick our equation. So do I know WF? No. Do I know WI? Yes. Do I know alpha? Yes. Do I know T? Yes. The first equation could work, but I don't care about WF, so let's not even worry about that. Oh, second equation has a WF in it. I'm not even going to worry about that because we don't have that. Okay, let's look at the last one. Change in theta. That's a no. Omega I, yes. T, yes. Alpha, yes. And T, yes. Beautiful. Let's use that last equation. So, again, change in theta is omega I times delta T plus 1/2 alpha times delta T squared. Okay. So, omega I is 0. Time is 14 plus 1/2. 0.1 times 14 squared. Cool. So I plug it in my calculator, and I'm going to get, okay, so I plug in my calculator, and I get 0.9 radians. Cool. However, it wants the answer in revolution, so we got our distance amount. Sorry about the last little spin. I sometimes accidentally just move the screen around. So let's convert radians per revolution. So let's see. Radians to revolution. There are 2 pi radians per 1 revolution. So to go once around, we will go through 2 pi radians. Cool. Because radians cancel out. Cool. We're left with what we need to do. So when I plug this into the calculator, I get 0.16 revolutions. Cool. So if you did not get that when you plug in your calculator, be very, very careful how you put something in. So like an example is, this is a silly mistake I see all the time. If you do 1 divided by 2 pi in your calculator, I bet a lot of you, okay, so we're looking at this. 1 is approximately 0.98, that's why I use 1, and 2 pi is 2 pi. So pi we know is approximately 3.14. So 2 times 3.14, that's going to be just double 3.14, so that's approximately 1 divided by 6.28. So I want you to think to yourself, should the answer be more or less than 1? It should be less than 1. And if I plug this into my calculator, it's like 1/6 of something approximately. I got 0.157, or sorry, 159, excuse me. So it would be 0.159 revolutions is what it would essentially be. A lot of people, I bet, when they plug this in, they get 1.57 revolutions, which, does that make sense? No, that does not make sense. Our answer should be less than 1. So be very careful. I bet you can guess what this silly mistake is. You got to put this whole bottom thing in parentheses to make sure, otherwise your calculator will think that you're dividing by 2 first and then multiplying by pi. But you're dividing by the quantity 2 times pi. So just keep that in mind. Very easy to make silly mistakes with those, but this right here is our answer, 0.16 revolutions. Awesome. Thanks for watching.